This is Lab 3, Black Hole. Lab 3 deals with determining the mass of a black hole that is being orbited by a star. The unique position points of the star give a trajectory that can be used to determine the mass. The forces given by the star can be split up into two components, the perpendicular that points towards the center of the kissing circle and the parallel that points in the direction of the motion. The net force I found for the star is 8.45 times 10 to the 28 newtons, and the mass of the black hole was found to be 1.22 times 10 to the 34 kilograms. Some of the fundamental equations that are especially used in the code include the change in momentum equation, which can be split into parallel and perpendicular components. These components have an equivalent relationship to the parallel and perpendicular components of the net force, and thus the net force equals the change in momentum over the change in time. And probably the most important in actually determining the mass of the black hole is the magnitude of the gravitational force equation, which is rearranged in order to find the mass. There is some preliminary information that needs to be inputted into the code before we can get to the bulk of the code. This includes my email, which the code will take and use to analyze the characters in order to develop a unique trajectory of the star. The mass is also needed to be put into the code, and the mass given is 2 times 10 to the 30 kilograms. And finally, delta T is set at 1 day, which translated into seconds equals 86,400 seconds. Moving on into the main portion of the code, it is one big while loop that has the goal of determining the net force as well as its parallel and perpendicular components. To start, Fnet is found by determining the change in momentum over the change in time. Then, F parallel is found by determining p hat and dividing it by the magnitude of dp over dt. And finally, by rearranging the formula Fnet equals F parallel plus F perpendicular, we get that F perp equals Fnet minus F parallel. In order to get a better visual, arrows are added to the forces to better understand how the forces change as the position of the star changes. Because the mass is so big, the arrow scale needs to be made very small. The next part of the code actually finds the mass of the black hole. The equation for the magnitude of the gravitational force is rearranged to solve for m2, which is the mass of the black hole. The final equation to the right was then translated into a code below, which prints the mass for each point on the trajectory, which can be averaged to find the approximate mass. The final results show that the mass, which is an average of the masses provided, is 1.22 times 10 to the 34 kilograms. Information on the forces of the star is shown to the right with an Fnet that is almost equal to the Fnet perp because of the small F parallel. Two questions are asked about this lab. The first asks to discuss how the parallel and perpendicular components of the change of momentum and Fnet differ. The answer is that, as seen in the code, Fnet is equal to dp dt, and subsequently so are its parallel and perpendicular components. This is because of the law of the conservation of energy. And the second question asks if the mass of the new black hole, if a new black hole is placed into the same location without changing the motion of the star, would it be different? And the answer is no, they would not be different. They would have the same mass because the trajectory of the star was unchanged. In conclusion, the mass of the black hole was determined based off information of the forces of an orbiting star and its mass. It's interesting how such little information can determine an unknown mass. Some discrepancies that could have occurred revolve around the computer and how the final mass was the sum of all the masses determined by the code. In the future, I would venture into picking different emails to see how the result varies.